Firstly, konnichiwa. Good afternoon, everyone. I would like to say thank you for the organizers of this conference so that I can also share my thoughts actually with regard to this interesting topic on green chemistry and sustainable future. It's good that Dr. Surimache and Dr. Gabar have already showed us some of the emerging technologies, particularly in addressing our decarbonization and circular economy challenges. But let me share with you my thoughts about how we can advance, how we can make use of the method of life cycle thinking or life cycle assessment specifically to support emerging technologies like waste to energy or that carbon capture technology that Dr. Sorimache has proposed. Because we know that all of these technologies are technically feasible, but the real question is, when we scale up this technology and when we commercialize it, what are the large-scale impact? What are the large-scale environmental impact in terms of resource consumption, environmental emission? And that's the core of this presentation. So in a nutshell, what I would like to share with you in this 30-minute presentation is that in a life cycle perspective, from the cradle to the grave, there are emissions at every stage of the supply chain. There are resource consumption at every stage of the supply chain, whether we talk about energy, fuel, biomass, water, land, metals, and non-metals. And in the field of industrial ecology and sustainable engineering, these waste and emissions in the form of solid, liquid, and gas are now considered new valued resource. So with the given the established and emerging technologies, we can convert this into value-adding products like what Dr. Gabar has mentioned, converting waste into bioenergy, biofuel. So that is already a possibility. And the point of that is that if we develop these value-adding products, we create new industry and new job markets. However, we are operating within the constraints of Mother Earth, the planetary boundaries. We need to take that into account when we design products, process, and supply chain. And we need to think about whether the chemicals that we are using in producing the products are really not toxic, not hazardous to the human health as well as to Mother Earth. And we need to respond to United Nations Sustainable Development Goal, which is the COP28. And we also want that we have enough energy as well as food security. And considering that there are a lot of interest in green chemistry and sustainable energy nowadays, particularly in scaling it up, we need to take into account that the population continue to rise, right? And we need also to enhance our economy, both nationally and personally. So it's really a big challenge to the next generation of scientists and engineers, because we need to advance this what we call green chemistry and green engineering. So in a nutshell, that is what I really want to share with you. And if you get the idea of that one slide, then the rest are details actually. And this is really the outline of my talk, which covers all the key points. So let's talk about briefly why we are in this problem, in this scenario. And the problem is that the existing society's economic system, the linear economy where we take, we make, and we dispose, where we make use of a lot of resources, whether it's metals and non-metals and other chemicals, but we dispose all of this to Mother Earth. And the Mother Earth is already complaining to us, and that is affecting our ecosystem quality, our health in particular, as well as the reduction of the available resources. So it's really challenging, because we now realize that there is interdependence and interconnectedness of the Mother Earth as well as the social economic system that we are in. So it really calls for what we call circular economy, where there are three basic R's that we need to consider. That is to reduce, reuse, and recycle. And let's have this global picture in terms of energy consumption. And the major contributor actually, and the major consumer of this is, we have there North America there, Australia, Canada there, Canada in this way, and Russia there, and the Middle East. And they are really contributing a lot of energy consumption, because for every BTU of energy consumed in the form of coal or petroleum, there is a corresponding release of carbon dioxide. And if we look the global picture of the carbon dioxide emissions, in terms of absolute terms, China and the United States are the major contributor. But if we divide that in terms of the population, the Virgin Islands and Gibraltar are the major contributor of this global footprint. But the United Nations is interested to really reduce this, what we call absolute carbon dioxide emissions. So if we're going to zoom in, what are the major industry that is contributing to the problem? Primarily is the energy sector, coming from the industry, followed by the transportation sector and in buildings. Although there are also a major contributor in the agri-food sector, but the major culprit really is the energy production. And if we really want to reduce the greenhouse gases as well as the impact to global warming, we need to focus on reducing our energy. And that is why there are a lot of interest in green hydrogen and renewable energy nowadays. So what's the solution? We are in this problem, this what we call, we are now talking about green chemistry, because we have this what we call linear economic thinking, which is a myopic, a reductionist approach, which has resulted to a lot of problems actually. And that is why the solution that I propose is that we change our mindset. We change our mindset, the way we produce and consume resources, chemicals, materials, and energy, so that we can avoid as much as possible waste and emissions, or particularly those toxic chemicals, those toxic metals that we are producing because of financial bottom line. So it's really questionable nowadays on why we have to be generating all of this solution. And it's good that green chemistry is really advancing in this field. So let's talk about the shift. Why we need to shift, why we need to transition. This call for sustainability, or what we call sustainable development, requires what we call a systems science approach or a systems engineering approach, where originally we want that there is like an equal contribution or from the triple dimension of sustainability. Or nowadays, we can still have what we call the Mickey Mouse approach, where still, the financial bottom line is the major actually focus of many companies. But it has been, we would like to argue in industrial ecology and sustainable engineering that the economic system is just a subset of the social system, and the social system is just a subset of the natural system or the Mother Earth. So in industrial ecology, we have this master equation actually, where let's say that the carbon dioxide emission or the waste is directly proportional to the population. So the higher the population of a country, the higher is the waste as well as the carbon dioxide emission. The richer is the country, then the potential of higher emission as well as waste is there. However, depending on the technology being used, like what Dr. Gabar and Dr. Saruri Matias put forward, if these are what we call the best available technology, then they can actually reduce our environmental emissions and impact. However, if we use obsolete technology, then that will also contribute worsely in terms with the environmental emissions. So the Mother Earth is really requesting all of us not to destroy her, so that she can give more oxygen, water, and energy that we need. So this is in line with the United Nations Sustainable Development Goal, and there are 17 of them. And I just want to focus on goal 12, really, which is really regarding on how we can minimize our environmental emission and resource consumption. And that is in alignment with prevention reduction, particularly in the way we use chemicals actually and waste that we need to address as much as possible. So let's talk about now the core of this presentation, which is the environmental life cycle assessment, which This can be applied across all sectors, processes, products, technologies, and supply chain. And the core message of life cycle assessment is we need to quantify and analyze the environmental emissions at every stage of the supply chain, from the raw material extraction to the manufacturing, to the distribution, and finally to the disposal. And that's the core of using environmental life cycle assessment. And this is just an example because all of us want to drink coffee. And therefore, in a life cycle perspective, from the resource extraction to the disposal, there are resource consumptions, or whether it's water, energy, metals, non-metals, and we need to use these resources in every unit operation actually, and then we assemble them, we package them, and then we use them, and then eventually we dispose them. And let's be aware now that at every stage of the supply chain, there are environmental emission and resource consumption. So this is just the snapshot if you want to use environmental life cycle assessment to analyze the environmental impacts of any emerging technology you are developing, whether waste to energy, plasma technology, or even this Dr. Sorimacha's idea of really reacting the carbon oxide with the CO2 to produce calcium carbonate. And really what we are interested, we are doing an accounting here of the input, which is usually the resources, and the output, which are the emissions to air, water, to land. And we express all of this into what we call environmental impact categories, particularly global warming there, eutrophication there. So there are a lot of environmental impacts, not only what we call climate change, but there are a lot of environmental impact that we need to take into account. So there are four major stages in environmental life cycle assessment. One is the goal and scope definition, where we need to establish what's the purpose of our LCA. Step two is inventory analysis, where we need to actually gather the necessary data and information so that we can make the analysis and actually convert this into what we call environmental impact categories. And then we interpret the results, because we're going to make use of the results in product design, technology improvement, actually, particularly even green marketing, and even to support actually government in public policy making. So there are already software packages there. I strongly encourage you that when you are developing an emerging technologies that make use of these software, pre-software packages, whether CMLSA or the Open LCA, or the latest one is the Brightway. So these are freely available. You can download this in your respective laptop and make use of this so that you can actually analyze what are the potential environmental impacts of your emerging technologies, as well as your emerging product systems, so that you can actually modify your technology to become environmentally friendly and to reduce its environmental impacts. So the method of LCA is really has a lot of applications, whether you go for eco-design, for cleaner production, for building materials. There are a lot of applications, and I strongly encourage you that those who are doing research in green chemistry and sustainable energy make use of the LCA method. So let's go into further detail in using this method. The first one is the goal of the study, actually, which is really we want to identify what's the purpose of doing an LCA. Is it really looking on the environmental emission as well as the resource consumptions for that specific product we are considering, whether we are comparing actual different emerging technologies, waste to energy. So I think Dr. Gavaras mentioned about there's biochemical technologies, there's thermochemical technologies. We can make use of an LCA to know what is the carbon footprint profile, what is the energy profile consumption of each of these emerging technologies. So there are a lot of opportunities actually to use LCA, and this can be used by company managers, purchasers, and designers actually. So it's really a very important tool nowadays. So once we have defined that, we also need to know the boundary of our research actually, the project, the LCA project. And you encounter the way do we have cradle to the grave or cradle to the grave, where that is the most comprehensive life cycle assessment. But depending on the availability of the data actually, and whether you can get data from specific technology, you need to reduce the scope of your study, whether it's cradle to the gate or gate to gate. So it's very important to take that into account. And this is just simple actually, because it's very important, the procedure of allocation. And the point here is that we need to know how much electricity is going to chlorine, to sodium hydroxide, as well as to hydrogen, as well as the salt, which is a resource, how much is going, contributing to chloride production, to sodium hydroxide, as well as to hydrogen. Because if in case we would like to analyze what's the environmental impact and resource consumption of the hydrogen production in this unit process? And we can do that via allocation, actually. So once we have defined the purpose, the goal of the LCA project, then we will collect our data actually in terms of environmental emission and resource consumption. And as you can see, it covers the whole life cycle, or what we call the supply chain, considering all the inputs actually at every stage of the supply chain, as well as the outputs. And we need to aggregate that so that we can analyze which one is contributing to the major environmental problem, whether it's global warming, whether it's acidification, and so on and so forth. And this is just an example of what they call a life cycle inventory data sheet, where it lists down all the materials consumed as well as the emissions. And then you can perform what we call scenario analysis to find out how could you modify the process or product in such a way you can minimize your impacts in line with green chemistry. Then after that, you proceed to what we call an impact assessment, where it's just simple classification. And these are all the environmental impacts that we need to take into account. But the most famous one is the global warming or the climate change impact or the acidification. So we can just briefly define here, if you don't know about global warming, anything that contributes to warming the global earth, and that is really expressed in carbon dioxide, whether it's a methane gas and any other chemicals out there, which actually, warming the whole earth. And that is what we call global warming. And secondly, when we talk about acidification, this is coming from the sulfuric acid and nitric acid from the industry to that results what we call an acid rain. So we need to take that into account also, and maybe alter some of the processes in our production system to reduce acidification potential. Eutrophication potential is a big issue in the agri-food sector when we use a lot of phosphates and ammonia actually, which are really contributing to this problem. Moreover, we have also the smog formation, which is a result of the ethylene there, which is usually coming from hydrocarbons and nitrogen oxides, which are contributing to this issue. And this is also human toxicity potential, the heavy metals, all of these are contributing also to this environmental impact category, and so on and so forth. And this is just a simple calculation actually, although there are a lot of software out there that can make all this calculation easily, but you can also use Excel sheet where you can have this, you can get this data from the step to the second step, which is the inventory. And then you just multiply that with this constant. This is widely available, the global warming potential, and then you just add them so that you have what we call a quantitative profile of any product system or any technology that you are analyzing. And this is just a sample result actually, after conducting what we call environmental life cycle impact assessment. And after that, you interpret the result, actually, particularly identifying which unit operations that are contributing to the problem, let's say, of global warming, and which specific chemicals we are using that are contributing to the problem of global warming, acidification, and eutrophication. And that's the purpose of interpretation there. So the idea of life cycle thinking is not really new, but it's really urgent now to apply this across all products, process, technology, and supply chains so that we can really minimize our environmental impacts and contribute to what we call a low carbon circular economy. And 3M is a very pioneering in this because they are a very chemical industry and they have already used life cycle assessment. So it's really a question of really expanding the application of LCA into different products and chemicals. And this, however, there are limitations in using LCA, particularly on the availability of data, which is a concern. And hopefully with the use of artificial intelligence and any digital technologies, we will be able to overcome these shortcomings also. And there are also issues that we need to take into account. So just to summarize this 30-minute presentation, actually, which is a lot of things here, is LCA is a system approach. And this will help you really on identifying and quantifying the environmental emission as well as the resource consumption of any technology, process, product, or supply chain that you are developing. And the intention of this is to redesign the products and process and supply chain and to maybe identify an alternative or substitute chemicals that we're going to use to produce a specific product. And there are 4 major steps in LCA: the goal of scope, the inventory analysis, the impact assessment, and the interpretation. However, we need a lot of data and LCA software, and hopefully artificial intelligence can be explored. I think that's it for me. Feel free to ask questions. These are my details. Feel free to contact me anytime.